Last class we have discussed the what is called LQG problems, and finally we have come with an expression that dynamic equation of the system or process dynamics and estimated dynamics, we have come across with this expression, where V of t, small v of t is the measurement noise. This equation can be rewritten into a error, that state equation augmented with a error equation, which will come into this form. And if you look at the equation number 12, you see this the matrix, this matrix is a diagonal matrix, and this we can control the what is called closed loop system eigenvalues and observer or estimated eigenvalues or Kalman filter eigenvalues separately. One does not depend on the others. So, this A of B k can be designed independently from the A minus L C of the Kalman filter gain. Both are controller gain and Kalman filter gain can be designed independently. That means, separation principle holds for this one. So, now let us look at this stage, that what about the its loop gain. That means, if you talk about the robustness of this controller, as we have seen in the what is called earlier case LQR controller design, when the states are we are assuming available to us, then we have seen that controller LQR controller gives the what is a good stability margin. That means, gain margin is varies from what is called greater than equal to half to infinity, and phase margin is greater than 60 degree. Whether these properties of the systems holds in case of LQG problem or not, that we will study now. So, that is called the loop transfer recovery. So, let us start with loop transfer recovery. That means LTR. And if you see this one and this loop, let us find out the loop gain of these systems. So, we know the our estimated LQG problem, we know our LQG problem, the estimated equation LQG problem, the estimated equation is dynamic equation is x dot hat x hat dot of t, this is x hat dot of t is equal to A minus B k minus L c x hat of t plus L of y of t. This L is the Kalman gain, Kalman filter gain, and this k is the controller gain. Agree? And where u is equal to with, you can write with u is equal to minus k x hat of t, u of t is equal to this. Now, if you take the Laplace transform of this quantity, that u of s is equal to minus k x hat of s. So, which you can write it, because this, even if you take the Laplace transform of this equation, then we will get it x hat of s, we can write it this minus, that will be a s I minus A minus B k minus L c, this whole inverse, agree. Then this will be a L y of s. Because you take the Laplace transform of this one, you will get it s I x hat of s. Then Laplace transform of this one is x hat of s. Bring to this side and take the value of x hat of s. Then x hat of will be s I minus as A minus B k minus L k whole inverse. This will be multiplied by L into y s. taking Laplace transform from this one, we will get it that quantity from this to this. So, x hat of s is replaced by this one from this equation by taking Laplace transform both sides. So, let us call this equation is 1 and we have s is equal to minus this whole quantity I am writing is k s into y s, the whole quantity from this to up to this is I am denoted by y s. So, now where we can write where y s is where k of s is equal to k s I minus a minus b k minus L c, this whole inverse into L. This is our K s. Now, let us this whole thing this we denoted by, let us call phi r of s. Phi r of s, this whole thing is nothing but a what is called regular resolve this phi r of s is called phi r of s is called regular resolvent matrix, regulated resolvent matrix, regulated resolvent matrix phi r of s. Agree, because this controller is there. If you see in this one, controller and observer gain matrix also involved in this one. That sense it is called regulated resolvent matrix phi of s. So, now this is, let us call this equation is, that is what is, we consider that equation is 2. This equation is 2. Agree? Now, if you draw this circuit configuration or block diagram form, this is our reference input R, which is equal to assume 0. Then this is our in transfer function domain, if you block diagram you put it, then G is, this is our plant, this is equal to S I minus A whole inverse B is nothing but this I am written by phi of S into B. This S I minus A resolvent matrix of this system is phi of S and B as it is. This is the, and this is our C matrix. The output of this is x of s, this is C, this is our y of s. Agree? And from this one we have a that our Kalman filter output of the Kalman filter is our x hat of s, and this is this. Agree? Then this will go with a controller gain, then this is minus of that one, and this is our u of s. Agree? And this inside this one, that Kalman filter structure is there, that means input information also there, output information also there. So, this is inbuilt in there. So, basically in transform domain it is a S I minus A minus B k minus L C, this whole inverse into L. Agree? That is our phi L into K, that will be our K of S. So, this is nothing but our K of S. See our K of S expression, K into phi S I minus A whole inverse L is the our K S whole thing. Agree? The whole thing is our, and this is our phi of R, the whole thing our K of S. So, now find out the loop, what is called, this is U of S, find out the what is called loop transfer function for this Kalman filter based controller loop transfer functions. So, if you loop gain or loop transfer function loop gain, let us call, we have denoted by L R of S, is nothing but a use from here to here. If you just move it here, this loop you break it, find out the loop transfer function. Just like in our basic block diagram, if you see basic block diagram, if you see, this is our G of S and this is our feedback path H of S and this is our minus this. So, this is Y of S. In order to study this one, then our sensibility or complementary sensibility loop transfer function, our loop transfer function is G S H of S. Similarly, in this case also we have a loop transfer function. If a loop gain of this one, I can write it, this equal to K into this quantity I have considered is equal to phi. This quantity, if you see, it is a phi R S into L, then C, then phi S into B. Agree? This is the loop gain of this Kalman filter based controller. When we have designed the Kalman filter based controller, the loop gain is K phi R, this is phi R, then L, then L, then C, then B phi. So, this is the loop transfer function. If you look carefully with the what is called LQR, there our loop transfer function is K phi S into B, because this filter is not present in the LQR. We are assumed that our states are measurable, all states are measurable. So, next is the, let us call this equation is 3, this equation is 3. So, next we find out the loop transfer function for the LQR problems. Loop transfer function or loop gain for LQR problem is equal to K into G S, which is nothing but a K into S I minus this or phi S into B, and this is nothing but a S I minus A whole inverse. This is our loop gain, and clearly you see this one, this loop gain of the Kalman filter based controller design and the LQR design, LQG LQR loop gain is different. And we have seen in what is called LQR design, that controller what we have designed the K controller design, the system what is called gain can be varied from K is equal to greater than equal to half, or you can increase the gain up to infinity from the present value of gain, whereas phase margin it will give at least 60 degree for the design gain K of the closed loop systems. So, that we have seen. In other words, if you draw the block diagram form of this one, it is look like this, G S and G S, this is nothing but a S I minus A whole inverse into B, that output will be x of S, and the states are all measurable. So, this and this loop gain, if you see the loop gain for this one, it is K into G S. G S is what? This is phi S, resolvent matrix of the original our given matrix, S I minus A inverse. This is the inverse of S I minus A this is inverse this. The two loop gains are different. So, we may expect that LQG controller, they may lose the what is called the excellent properties of LQR. What is the excellent property we got in LQR? Excellent property in the sense of gain margin and phase margin, what we got it, we may lose that one. So, remarks. LQG does not have the same properties as LQR design method. Due to the introduction of Kalman filter, because the loop gain is different and that part is coming additional. This part, if you see this part from here to here, from here to here, this from here to phi L S L C, this part is coming extra, and this is definitely there will be role of what is called gain role as frequency is changing. So, first remarks is this one. Second, it has lower stability margin, it has lower stability margin than the LQR design. And sensitivity properties, that means sensitivity properties are not good as those of LQR. Sensitivity properties are not good as that of those of LQR design. Because sensitivity stability margin, that means gain margin will lose, it will not able to maintain as we got LQR problems due to the introduction of this Kalman filter. Okay. And not only this, that sensitivity, disturbance rejection or noise rejection case, it will not be good as it is in case of LQR. This is 2. Third one is it is possible to recover the what is called stability margin or good properties of LQR, what we got it, that properties we will be able to recover while we have designed the LQR design. Agree, LQG problem, when you have designed the LQG problems, we have seen that there is the loss of what is called stability, stability properties, the stability margin it will be reduced. So, that we can regain or recover by introducing some noise in the process signal. So, it may be possible, it might be possible to recover some of the desirable properties like gain and phase margin. LQR by selecting the noise, process noise by selecting the process noise covariance matrix, variance matrix. Let us see how we can regain our what is called stability margin by introducing what is called selecting the process noise covariance matrix. So, let us define. There are some mathematical manipulation we have to done, and we have seen how the process noise, if you can select properly, then it is possible to regain the stability properties of LQR. So, define the following quantities. It is conclusion is that if you design the LQG problem, that stability properties of LQR is not retained. Agree? So, we can able to recover this stability margin of LQR by introducing or by selecting the process noise covariance matrix. So, let us define phi of S is equal to S I minus A inverse, that is the resolver matrix of the system. So, next we consider phi of C is equal to S I minus A minus B k whole inverse. With this identities, with this symbol using in equation number 1, let us see equation number 1, this I will use that one. Then what will in this equation I use the phi C. So, from 1 loop gain not 1 loop gain expression this is the loop gain expression, this from equation 3, from 3 loop gain LR is equal to K, then you have a, that is if you see this one S I minus A minus B k minus L C whole, then whole inverse that the whole inverse minus L, agree. So, this L, then phi of S into B. So, this I can write it this K into S I minus A minus B k, A minus B k, this I am clubbed together A minus B k plus L C whole inverse L, then C, that I missed here C, then phi of S into B. Agree? So, this equation I can write further L R of S then I can write it this, that this part you see S I minus A, this inverse is a your phi C, that is what a phi C. So, I can write this is nothing but our phi C S inverse plus what is left L C, agree, then whole inverse L C into phi of S into B. Let us call this is equation number 4. So, from this equation this is equal to I have written phi C inverse then L C this one. So, this and using now in equation 4 we will be using one matrix inversion lemma using matrix inversion lemma. What is this matrix lemma? Let us call we have a matrix A bar, B bar, C bar and D bar. Whole inverse is equal to A bar inverse minus A bar inverse, then your B bar, then D bar, then A bar inverse, then B bar plus C bar inverse, then whole inverse, D inverse, D bar, A bar inverse, this one. This matrix inversion can be written into this form. So, you are using in this expression this matrix inversion lemma. For that one we set A bar is equal to phi C inverse of S, then B bar is equal to your L and C bar is equal to your identity matrix and D bar is equal to C. So, I will use this lemma in this inversion. So, our using this one in equation 4 from 4 using the above lemma in 4 we get L R of S is equal to, then this is phi inverse of A, okay, A bar. So, our you see A bar phi inverse. So, this is phi C of S, agree, phi C of S, then minus, and you see this one there is a k is there, k is missing here, k bracket minus A bar inverse, that means phi C of x S, B bar is what L, then bracket D bar is what C, A bar of this phi C of S, B bar is what L, then your C bar is I. So, this whole inverse, D bar is what C and then A bar is phi C inverse, that inverse is phi C of S. So, this equation is rewritten into this form, into that into star into L C phi of S into B. So, this equation is complete now. Now, we are doing some manipulation of this one. So, I push it, see this one, I push L in this expression, agree. So, phi C L and this L will also go here. So, phi C L. So, if you take it phi C S L common, then it will be remain here I minus. So, this will be a I plus C phi C S L whole inverse, then C phi C S into L, agree, into L bracket closed, then C, because L I pushed inside. So, remaining part is C phi of S into B, agree. So, this now so, this I can write it further, I can write it this phi C S into L So, what will come here? Phi C L this, and this I can write it, this I can write it this matrix into inverse of this matrix. So, I am taking common of that inverse of this matrix I C phi C x L whole inverse. Then what is left here? Because I am writing this matrix into I plus C phi C L. So, it is left is I C phi C S into L minus this one left, because this I have taken common C phi C S into L. So, close this one, then C phi C S, then C phi of S into B. So, you see this cancelled. So, ultimately it is we will get it here. If you see this one, the simplification, that LCR L R of S is equal to K phi C of S L I C phi C of S L whole inverse C phi of S B. Again, this is the equation. Let us call this equation is equation number 5. This is the equation number 5. Now, recall our what is called our basic equation, system equation. If you recall our system equation, recall the system dynamic equation, system dynamic equation. From just recall from our previous lecture, the dynamic equation. So, our equation number 1 there. So, x dot is equal to A x plus B u plus gamma w of t. So, in the process in the system equation, this is the process noise w of thing, process noise. Again, we know the and its dimension is, let us call it dimension r cross 1. Other dimension we have already specified in our previous statement of the LQG problem. So, this process noise covariance matrix. So, if you recall this one. So, now in LTR loop transfer recovery approach, loop transfer recovery approach in loop recovery, it is assumed that the process noise covariance matrix, that in the process noise covariance matrix we have considered W in our last lecture matrix is nothing but a, from here you see it is a process noise covariance matrix gamma W into W transpose is equal to Q, that gamma transpose. This is the noise covariance matrix of W, or noise covariance small omega, that is Q. Agree? So, this is the noise covariance matrix. If you recall our LQG problem statement, W is the process noise and its covariance matrix is your Q. So, since it is going through a channel W gamma, so the noise process covariance matrix, process noise covariance matrix is gamma Q gamma transpose. So, this is replaced by now by gamma Q gamma transpose is now replaced by gamma W 0 gamma transpose plus small q B into B transpose. Okay. This is any positive scalar quantity and the gamma 0 is the initial guess of process noise, initial guess of process noise covariance matrix, process noise covariance matrix, initial guess. Okay. So, let us call this is equation number 6. Now, using this expression in our algebraic Riccati equation of Kalman filter, using this equation, then equation 6 in ARE, algebraic Riccati equation of our Kalman filter that we have discussed last class. If you see this one Kalman filter, then we have it is the dual of what is called algebraic Riccati equation of controller design. So, here there is A transpose P, here it will be A transpose replaced by A. So, A P E for algebraic Riccati equation for the Kalman filter and this is the error covariance matrix. Agree? Then P E, please refer to our last lecture note. So, P E, then there is P B, B is transposed by C transpose. So, this B P B R inverse. Agree? Here is measurement noise covariance matrix, this one P B R inverse B transpose means C, then P plus gamma 0 gamma transpose plus q square B B transpose is equal to 0 and that quantity is nothing but our gamma q gamma transpose. Again gamma q gamma transpose. So, this is the algebraic Riccati equation for the Kalman filter of that one. So, let us see what we have considered Q or W. I am not able to recollect what is considered. Let us see in the algebraic Riccati equation of the Kalman filter, the noise covariance matrix what we have considered. The noise covariance matrix I think I have considered W. So, better this is W, I have considered there W. So, this is W, agree? This is W, because earlier I have considered W. So, please write it same notation here W. Noise covariance matrix I have considered is the W there. So, this gamma W terms is now replaced by a two parts. One is the initial guess and another is Q transpose this one and this is a positive semi definite matrix, that is one. So, all these things and W is a greater than 0 means positive definite matrix. So, this equation we can rewrite by dividing by Q square. So, if you divide by Q square, that means A P E P suffix E Q square P E suffix Q square, this is whole A transpose, then P E Q square agree, that I am dividing by C transpose V inverse, agree, C P E. I divided by q square multiplied by q square, it does not change anything. So, that will be a gamma W 0 gamma transpose q square plus B transpose is equal to 0. Agree? Let us call this equation is equation number 7. This equation number. What I did it? I divided by q these things. So, now we made an assumption. The plant we have assumed is minimum phase system. The plant is, if the plant is minimum phase system, means all zeros are stable and B and C full rank with number of inputs is equal to number of outputs, V p is equal to m, number of outputs is equal to number of p. Then one can write it limit q tends to infinity P e divided by q square is equal to 0. Why? The way we are increasing the q, we are the P e is increasing more slowly than covariance matrix Q is increasing. And which in turn, when Q is very large, that will tends to 0. That means, if we increase in the Q, again the P is increasing, the error covariance matrix P is increasing more slowly than the Q is increasing. So, this implies that this will be Q is very large infinity, this will be 0. So, now from equation 7, if you use this expression in equation 7, what is the logic behind this? Q, the way Q is increasing, the increasing in P is more slowly than increasing in Q. So, with this logic, we can rewrite the equation from 8 or from 7, sorry. From 7, you can say this is 0, this is 0, this is 0, but this quantity is 0, but you see P is also increasing. So, this part I cannot write is a 0. So, what is the term is left here is q square P e by q square C transpose V inverse C P e q square. See what part is left? This part C B square into q, agree, minus B transpose is equal to 0. Because q cancel, now this is approaching 0, but P is also large. So, I cannot write this is equal to 0. So, further we can write it, if you see this one, that q square P e by q square C transpose V inverse C P e q square tends to, this I can write it tends to B transpose. When q are increasing, that this tends to, this quantity tends to B transpose, which I can write it also P e C transpose, this is not transpose, this is B inverse. C transpose V inverse, agree. Then I can write it V into V inverse is the identity matrix, this is identity matrix. Then C P E into 1 by Q square tends to B transpose. This I am writing just this cancel, then I am writing. This is, if you see, this is nothing but a Kalman gain L. So, this will be a L, that will be also V is there. If you see this one, this L, and this will be your L transpose, and this is V. So, I can write it that L V L transpose, this is L. So, from here to here this is L transpose, then V, and 1 by Q square tends to be V transpose. Then V is a noise covariance matrix of the measurement noise covariance matrix. So, I can write V half L, V is a symmetric matrix, this, and I can write it V half, agree, L, this I can write L V half whole transpose tends to B transpose. Because B is a symmetric matrix, the square root of B I am writing V half transpose, then manipulating this one I am writing this one. So, and there is a Q square, one Q I keep it here, another Q I keep it here. So, this expression remains same. So, if you look at this expression number 8, the general solution, this quantity tends to be B transpose. If you select the L, if we select the general solution of equation 8 is L tends to, when L tends to Q B B half, L tends to be V minus half. If L is Q B B minus half, minus half plus half is cancelled. So, that will be a B Q cancel. Similarly, this B, so B transpose will approach. If your selection of this one L solution is that one P half, as Q tends to infinity. So, that is the solution of is that one, then Q B inverse of this as Q tends to infinity. So, substituting using this value 9, using equation 9 in 5 or LR expression, the loop gain expression of LQG expression. So, I am using loop gain expression. In this expression, I am using the value of L is what? Q B and V half, that means square root of your noise covariance, measurement noise covariance. If you use this one in this expression, we get L R of S is equal to K phi C S. L in place of L I am writing Q B minus half, then bracket I C, then phi C of S Q B minus half whole inverse, then star multiplied by this C phi of S into B as Q tends to infinity, as Q tends to infinity. Look, this is our L, we are substituting L, this is L and this is our L in the expression 5. So, this further we can write it this finally we can write it, since this is the large quantity of this one compared to 1 in diagonal elements, then we can neglect this one compared to this one. So, that tends to phi C of S q phi C of S q, then V of half, then C phi C of S q B half whole inverse star C phi of S B as q tends to infinity. Now, look at this one, this is inverse. So, q cancel, then V is the identity matrix. So, this expression finally will come, if you see, if this expression finally will come k phi C of S B, then C phi C S B phi C S B whole inverse C phi of S, this is phi of S B as it is. From there C phi C B inverse this as q tends to infinity. Agree? Let us call this equation is equation number 10. Okay. So, now we are using another identity in this expression 10, using the identity phi C of S we know is nothing but a S I minus A minus B k whole inverse, which I can write it S I minus A this plus B k whole inverse, which I can write it, this is nothing but a phi S inverse, this one plus B k whole inverse. So, I can write it, this is nothing but a, if you write it this one phi of I phi of S, phi S if you take it common, then I B k phi of S, I B k phi of S whole into phi of S this inverse. So, push it phi B k, this is a phi x. So, this is nothing but a phi of S, because A into B whole inverse, B inverse, A inverse, reverse order. So, this inverse is phi of S, then it is a I plus B k into phi of S whole inverse. So, this let us call this equation number 1. This identity I am just writing S I minus A minus B k inverse, I can write phi S plus 1 plus B k into phi S whole inverse. This expression I am using in equation number 12, 10 sorry. So, using 11 in 10 is this one, wherever there is a phi C I will use that one. Using this one in 10 we get L S of this is k phi S into I plus B k phi S whole inverse B C phi S into I plus B k phi S whole inverse, this whole inverse into B. Look at this expression, this k phi C I am using that one phi S, this expression is nothing but a phi C of S. Then your what is this expression B I have written, then B I have written, see this one B I have written, then C phi C expression is what, from here to here is phi C expression, this is phi C. Then B agree. Then this multiplied by these things, then this thing multiplied by C phi s of B as q tends to infinity. Let us call this is equation number 200. That means, in equation number 10 I use this expression phi whenever there against phi c is there, I am using in equation 1 and we got this expression. So, finally, and once again we are using this identity, I plus b k phi of s whole inverse b, you can write it this reverse order b I plus k phi s b inverse. So, I plus b k phi s whole inverse b is a b, I plus b will go later phi s this. This identity I am using in this identity using in 12, we get that limit q tends to infinity L r of s is equal to k, say in phi k phi s, then instead of that one, instead of this this I am using the identity that one b first, then I am at b, then I plus k phi s into b whole inverse star. So, this is then b, agree, C phi s, that is it, then this identity I am using, this part identity. So, that is b, that will be b, then I plus k phi s into b whole dash inverse b, this I plus this, that inverse is here, agree, that inverse is here. So, this inverse is here, inverse, then whole inverse, this inverse into C phi s b. So, what is left in there? This will this inverse, and again that I missed something. So, this will be finally, it will be, because we have considered that the number of inputs and output is same. So, this inversion is exist, that whole inversion is exist, this inversion exist. So, ultimately we will see, we will derive this thing in next class, some 2-3 lines is left. So, we will discuss in this next class that what is the our choice of that our loop gain choice through noise process, what will be the ultimately loop gain will come. It will come same as the linear quadratic regulator loop gain. So, one can regain or recover the loop gain of LQG by selecting the properly the process noise covariance. So, the rest of the portion we will discuss to next class.